Well, yeah, so it's my pleasure to introduce Roger Casals. So title of his talk is Applications of the Relation Between Cluster Algebras and Symplectic Topology.
Thanks, Skylar. Well, thanks again. Thanks to the organizers, and thanks again to all of you for attending. Yeah, so this second talk is more about assuming that whatever said in the first talk, whatever Dapping said and Jose said, all works fine. And then trying to use that bridge, that connection between cluster algebras and Lagrangian fillings, so as to deduce some new things that maybe we didn't know before. And you're welcome to ask any questions about the prior things, but this is more a talk about forward and the future. So again, the theme is to understand how that interaction can be used to prove some results, have a better understanding of symplectic topology in this four-dimensional setup. And two natural directions are, well, suppose I now have this cluster algebra and I go talk to cluster algebra people, Sergei Fomin, Lauren Williams, Zolovinsky, like all the results that they have. Well, what can I extract from that? And one immediate result you can extract is the construction of infinitely many Hamiltonian isotopy classes. So that has a geometric input that I will explain for you. You build these infinitely many candidates, but then once you've built them, can you just say, oh, by cluster algebra theory, by results of Fomin, Zolovinsky, by results of other people, that immediately implies that these infinitely many Lagrangians that you've built are different. And that will happen. That's one way to go about it. A second comment is this moduli space that I discussed, this moduli space of pseudo-perfect objects of the partially Raphukaya category, or if you wish, the moduli of sheaves, actually has interesting geometry. It's a nice affine variety in our case. Can you compute its cohomology? Can you say things about its geometry? And we'll be discussing the fact that by virtue of being a cluster A variety, it automatically comes endowed with an holomorphic symplectic structure. So then you can start to do geometry on this B-side mirror of these Legendrians lambda. So I'll discuss these two aspects. Again, neither of them is easy if you didn't have cluster algebras. Both of them really work well with the cluster algebra structure. And then you can go the other way around. So now you can say, well, suppose I was interested in improving things about cluster algebras. Suppose I was interested in showing that something is indeed a cluster algebra, or I'm trying to access some seats through some combinatorics. Does symplectic topology, does the theory of weaves help you in that way? And the answer is yes, it does. It does in a series of ways. First of all, it allows you to construct cluster structures on spaces that were only conjectured to have them. The more general statement is what Jose will prove, which is we can build cluster algebra structures on braid varieties. But in particular, we recover the case of Richardson varieties, and that relates to a conjecture of Leclerc, where these Richardson varieties were discussed and in some cases proven to have cluster algebra structures. And there's beautiful work by Leclerc himself, and then Christina Sherienko, Melissa Sherman-Bennett, and Lauren Williams, and other people. But now this weave technology allows you to give this sort of independent proof, symplectically inspired proof that actually generalizes all known results to date. And a second thing is there's many properties about cluster algebras, reddening sequences, Donaldson-Thomas transformations in a more geometric manner that are interesting. Do they exist? Can I build them? And symplectic topology gives you ways to do that. So weaves will do that for you. And the last thing that it's particularly relevant with regards to combinatorics, say you want to do cluster algebra, say you really want to just care about constructing cluster algebras and studying them, many of the combinatorial models that exist to date, such as Plavik graphs, can only access infinitely many seeds, where typically there's infinitely many seeds. So is there a combinatorics, is there a way to do combinatorial sort of geometric representation theory and access all these seeds? And beautifully enough, weaves do that for you. So weaves are a way of diagrammatically encoding infinitely many seeds and do so in a manner that expands, not just sort of parallel to it, but generalizes the known combinatorics of Plavik graphs. So I'll be discussing these applications today, and there's others. So you're welcome to ask about them. As I said, you can use them to prove things in about spectral networks, some higher dimensional topology, so on and so forth. All right, so I'm going to delve first into this explicit construction of the infinitely many Lagrangian fillings. Okay, so the goal is the following. So you set yourself with your Lagrangian, you assume it's of the form lambda beta, and then you ask, can I build Lagrangian fillings for it? Well, yeah, we've discussed that, and then with L compressible system. But we want to build more. Well, maybe you can do that in at least two ways. The first one is a very geometric construction, and it's the one I'll be focused on. And the idea is the following. Suppose that you found, and this is the key thing, a contact isotopy that brings lambda back to itself. So you found a way to move your Lagrangian around until it goes back to itself on the nose. Then, because it is the time one map of a contact isotopy and invariance of the Lagrangian invariance, by definition, that defines for you an automorphism of this affine variety. It defines a self-equivalence of the category, and therefore, yeah.
Sorry to interrupt you. Just to check, are you progressing on the slides right now?
Yeah, I'm where it says building infinitely many slides.
At least on my end, I still see the title page.
Oh, that's bad. That's very bad.
Yeah, just
okay. Well, I'm sorry. What do you see now?
that's better.
Okay, sorry. So all my blabbering was going through this before. So
In focus.
can you see the slides now? Is there some business going on? Okay. So what I was saying before is you can use this bridge to prove. Are we back again? Oh my. Well, I don't
There we
know.
go.
All right. So all I was saying was there are results in symplectic topology, which is these ones I'm mentioning here, and in cluster algebras, and that's what we will do for the next 15 minutes. So to sort of do these applications, and then I was already in this part of the slides where you have your Lagrangian being given to you, and you try to build infinitely many Lagrangian fillings. So the first thing you can do is as follows: is you create what we call a Lagrangian loop. So you have your Lagrangian here, in some way here, and you start moving it around with some Lagrangian isotopy until it goes back to itself. By virtue of being a Lagrangian invariant, the category of sheaves gets induced to self-equivalence. And therefore, when you take the moduli, you get an automorphism. And you can check through our construction that this automorphism is a cluster automorphism of this affine variety. So now, how do you build infinitely many fillings, or at least candidates, from that? What you do is exactly take a given filling, your favorite one, and then you attach to it the trace of this isotopy. So you take this isotopy that goes around, and you take the trace of it, this is a Lagrangian concordance, it's a cylinder, and then you attach it to L. And you can attach it 1 time, 2 times, k times. And a priori, these are candidates for different Lagrangian fillings. Well, now you need to prove that such Lagrangian loops exist, and that actually you can build them in a way that this guy has infinite order. If you do that, then you're good to go. And I'm going to focus on building those first, and then I'm going to say mostly, then cluster algebra tells you that this is going to have infinite order. A quick second comment, which works sometimes, is that you can, instead of using Lagrangian loops, just use mutation sequences, meaning suppose that you've built your Lagrangian filling L, and you have your L compressible system. So this is the situation I was describing before. You have this disk in here, you have this other disk in here. Now you can start saying, oh, I'm going to mutate, do Lagrangian disk surgery in this disk, and then in this other, and then in this other, and then in this other. So now you can have an infinite sequence of Lagrangian disk surgeries. And as long as you know that every time that you do the Lagrangian disk surgery, the L compressible system stays an L compressible system with embedded curves, then you can iterate that infinitely many times. So we found examples of that with Eric Zaslow in, I think it was in the original Legendre Wave paper already. And you can use that to create infinitely many candidates for Lagrangian fillings. And in fact, Lagrangians in Weinstein manifolds in that way. But now, of course, you have the task of showing that they're different at the level of Hamiltonian isotropy classes. So let me explain how to build these Lagrangian loops. In general, it's not obvious. Like, how do you find interesting Lagrangian isotropy that's going to bring lambda to itself? So here's a general construction that tends to produce interesting Lagrangian loops. What you do is the following: is you take a component of your Lagrangian link, lambda beta, and thicken it to a bunch of strands. So for instance, here you take this component in here, you have some Lagrangian in there, and now you thicken it. You thicken it so it has now 3 strands. So now you have these 3 strands that come from the previous strand in here. And now in these 3 strands, you put whatever braid you like in this case, 3 strands. But if you thicken with 7 strands, you can put a braid in 7 crossings in here. So we call this gamma here the purple box. I don't know, it's just because I drew it in purple the first time I was drawing this stuff. And then what you can do is, in this Lagrangian, take this purple box and move it around. You move it around past this beta in here, move it around until it exits the other way. Because it all came from this component here, you know you can go past beta, and then you go around, and you bring it back here. So this is a way to create links, typical links that have these particular loops, we call them theta loops, that allow you to go back to yourself, and potentially they give interesting self-equivalences of the category. And indeed they do. A quick comment, you could do just the unknot to begin with, and just satellite with whatever beta you wanted. So this is comment number 2. For any knot, this doesn't even have to come from this construction. You can just move the whole box around until it goes back to yourself. So that's a sort of something that's more general, but it won't always be of infinite order, even if there's infinitely many seeds. Okay. So this purple box construction is there. This is something that we introduced with Lenny Ng in one of our recent papers. And you now want to be computing whether these things actually induce non-trivial automorphisms of the cluster variety. So yeah. So let me give you a particular construction that is very geometric, and I want to give it here because it's in none of the papers that I've written, but it's really in my head all the time. So let me just explain a geometric way to create such Lagrangian loops. So what you do is you take S3, so this is S3 for you here, you have S3, and you project it down to S2 with a hop vibration. Just this is the hop vibration, just smoothly. Now, if you take like 3 points or say 4 points here, the fiber, it's going to be like 4 unknots, and they're linked according to a T44 torus knot. So now what I claim is that smoothly, it's certainly true that now I can act here with the mapping class group of S2 punctured in 4 points, and that's going to act on symmetries of S3 that preserves this T44 link as a link. It doesn't preserve the components, but it preserves it as a link. So more generally, you can do that for a torus, which is not just KK, but KKN. And if you have the mapping class group of the K-punctured sphere, the following 2 things are true. There exists a non-trivial automorphism that goes into the fundamental group of the space of Legendrians isotopic to the KK, the max trivial representative of the KK torus link. So that's the first thing. And the second thing is you can also do it with K, Kn. So with K, Kn, you are not going to have exactly the mapping class group of the punctured sphere, but rather you're going to have, I don't know why this is, yeah, there we go. You're going to have the braid group modulo its center, which really is a subgroup of the mapping class group of the sphere. So here's a proof for that. All you need to take is the smooth picture that I said before. You construct this hop vibration in here. You project down to S2. And now you want the Lagrangian to be in the fibers. So you take these 4 points in here. You have this knot in there. And you want this to be Lagrangian. So all you need to construct is a Lagrangian hop vibration. So this is a map from S3 to S2 with Lagrangian fibers. It's a nice exercise to show. I typically use it, do it using the quaternionic structure in S3, the IJK structure, that half vibration exists. You can just take the standard one, which has transverse not fibers, and then multiply by J. And then you get a Lagrangian half vibration. So now you take K points, and then the max TB representative of the KK torus length is exactly the preimage of these K points. And the morphism just follows immediately, because now I just move the points in the base, and that permutes the components for you. Now, the fact that this is actually a Lagrangian loop that comes from this purple box, that's something you need to check by hand, but it's doable, and it's explained in some of the talks I've given online, but it's a nice computation. For the general case, well, you cannot just take the half vibration as is. You need to modify it so you get a cipher vibration with one exceptional fiber, so that now when you take K points and you look at the preimage, you don't get the KK torus length, but you get the K, KN torus length, which again is going to have K components, but now they're just linked in a more interesting way. Two of them are linked not as a hop link, but as like 1, N cable. So that's a very natural geometric construction, just by taking the mapping class group of a surface, producing interesting Lagrangian loops. And these were the first examples of loops in the literature, in my work with Hao Gao, that produce infinitely many fillings in the case of torus links and others. So that's really what's going behind that construction, despite, you know, the paper explains it in somewhat a very technical way, but that really is the geometric intuition behind it. So that's a nice set of examples for Lagrangian loops. And in general, I can tell you exactly how it acts on the moduli of sheaves. So in this case, this moduli M for lambda K, Kn is just the top dimensional positoroid stratum in the Grassmannian K, Kn plus K, which really just translates into, you have matrices here. You have, so these are K, Kn plus K matrices, which you can just think as being vectors which live in CK. So each of them is a vector that lives in CK. So there's K rows, and there's exactly Kn plus K of them. Now, for them to be in the top positoroid stratum, there must be some transversality conditions. And for the top positoroid stratum, these are easy to describe. All that you ask is that the ranks of K consecutive ones are non-vanishing. So if you take the Plucker 1 through K, that's non-zero. If you take 1 through K, all the square matrices consecutively, you want that to be non-zero. In fact, the product of all these consecutive Plucker equal to 0 cuts out an anti-canonical divisor in the Grassmannian. So it is a representative of the anti-canonical class. It's a singular representative, but it's a good representative at that statement. So you remove that anti-canonical divisor, and what remains is this top dimensional positoroid stratum, which is exactly the moduli space that you have. So very, as I said before, very explicitly described, a bunch of vectors in CK. And now you go and compute, because of the weaves, because of the way you've built everything is very computable. And here's a lemma. How does the Artin generator sigma I in the mapping class group of the puncture sphere act? So that's the generator that changes two points next to each other. It acts exactly by leaving all the vectors the same, except the two vectors in the ith position. You change them, you move this guy to the left, and you move this guy to the right, and kind of like a Hurwitz move, nothing happens to the guy that goes left, but something very interesting happens to the guy that goes right. You substitute it by this intersection. And you do that cyclically in the windows for I, the I window, the I plus K, K, and so on. And so this is a very explicit action. You're really just talking about vectors in CK and some operation that exchanges two of the vectors, changes the order, and one of them gets exchanged by some other vector. So that's very precise. And because of this explicitness, now you can start to show that these things are non-trivial. So by studying this action, again, this very explicit action, you can start to say, how does this pull back the regular functions that I was discussing before, that Dapping discussed, these microlocal merodermies? How do they change them? And you can show directly that that change is indeed of infinite order. Namely, there are some cluster variables that some of these regular functions that when you pull back, You pull them back, you never go back to yourself. So they really always give you different elements. They produce different ideals in the ring of regular functions. And that gives you that this is a cluster automorphism of infinite order in there. There's different ways to show that. There's beautiful work by Chris Fraser explaining that in detail. But again, what's important here is you have this explicit description of the regular functions, this explicit description of the action, and these regular functions and the action behave nicely together. Namely, when you pull back the regular functions through these self-equivalents, you really can describe what the result is. And that description is very combinatorial, and you can show that it's of infinite order. So I should say maybe in general, this is giving you, so Z worth of generators, one for each Artin generator. In general, you can do even better. So in my paper with Hong Gao, we did already for 3.6 a bit better. So we actually showed that the whole action of the break group on 3 strands mod Z is faithful. So you not only have like infinitely many Lagrangian fillings, like there's an interesting structure within those Lagrangian fillings, and it's more than just Z, like some interesting number. Anyway, so now you say, okay, you've been discussing torus links. What's the deal with them? Well, torus links are simple enough that you can compute directly, and they have the advantage that once you've produced infinitely many fillings for them, then you can show that for any Lagrangian covariism up to some other Lagrangian, you can concatenate your infinitely many Lagrangian fillings for the torus knot or the torus link, and they will still be different. So for any Lagrangian knot or any Lagrangian link that you can find a covariism down to a torus knot or a torus link, if that torus knot or link has infinitely many fillings, sort of detected this way, that new Lagrangian will also have infinitely many Lagrangian fillings. So torus links starting with 3.6 and 4.4 are the first ones that have infinitely many fillings detected in this way with these Lagrangian loops. And that implies that many of these lambda betas also have infinitely many fillings. There's a more precise statement in recent work by Gao, Shen, and Wang that actually tells you exactly when lambda beta has infinitely many fillings and when you would expect not. So that's kind of the summary about Lagrangian loops. And yeah, I'm going to just comment on some of these constructions. Are there any questions at this point, though? All right. So the first comment is these infinitely many fillings are smoothly isotopic to each other, even Lagrangian isotopic, but they're not Hamiltonian isotopic with compact support. So really, this is a symplectic topological business. This is an important comment for people who understand smooth topology enough that they realized, oh, wait, the loops that you were describing actually maybe act non-trivial in pi1 of the complement. So smoothly, those concordances were non-trivial, already smoothly. Yeah, but surprisingly, once you concatenate them with the Lagrangian filling, they become smoothly trivial. So at the level of Lagrangian fillings, you don't ever change the smooth isotopy class with this construction, but you do change the Hamiltonian isotopy class. Okay, now a more direct application to some maybe more familiar setting for some of you. Suppose you don't care about Lagrangians, suppose you just care about Weinstein 4 manifolds. Well, there's a natural Weinstein 4 manifold that you can obtain from a Lagrangian by attaching handles to it. Suppose that your lambda is a knot for a second, then your 4 manifold literally is at the homotopy level S2, because it's the cone of the knot, that's a fine topological model, plus the 2 handle, so that's just an S2 at the homotopy level. So there are a lot of Weinstein 4 manifolds homotopic to S2 that you can just build by attaching a 2 handle on a Lagrangian knot. Now, these infinitely many Lagrangian fillings that I've built for these knots, actually, and this is a bit more effort, but that's done in my paper with Lenny Ng, you can show they still are different when you attach this 2 handle. So what have we done here? What we have achieved is we've constructed Weinstein 4 manifolds, the homotopy type of just S2, which typically have no embedded exact Lagrangians of genus 0, no spheres, no genus 1, no genus 2, and then you hit exactly the genus where you have the infinitely many fillings, and then there's infinitely many Lagrangian surfaces, closed exact Lagrangian surfaces all smoothly isotopic to each other, but all Hamiltonian different to each other. So for instance, if you take something like the 3-7 torus knot, the 3-7 torus knot has a genus 6 filling. So if you attach a Lagrangian, a Weinstein 2 handle along the max TV 3-7 torus knot to the 4-ball, you have a Weinstein manifold, which has no Lagrangian spheres, no genus 1, 2, 3, 4, 5. And then suddenly in genus 6, you have infinitely many Hamiltonian isotopy classes within the same smooth class of a genus 6 embedded exact Lagrangian. And I made a little comment here about then twists because I don't know, in my head, or at least when I was a student, I was always told, oh, then twist is the way to get more Lagrangians. But these guys don't even have Lagrangian spheres, so there's no such thing as then twisting. So there's something else going on more subtle than then twisting that allows you to produce these Hamiltonian classes. All right. The last comment is something that I mentioned a bit in the first talk, which is the way these fillings are built and the way these fillings are distinguished hints at the fact that at least for those lambdas that are of the form lambda beta, we might have a reasonable conjecture on what to expect. And in fact, there's this ADE type conjecture that this is written in the Viterbo 60 paper. I think it's called Lagrangian skeleton plane curve singularities, where this is stated. For knots that are 2n torus knots or 2n torus links, you would expect a Catalan number worth of fillings. For dn, which are also 2n with a double meridian, you would expect a different kind of Catalan number of fillings. For E6, which is 3-4, and for E8, which is 3-5, you would expect also some finite numbers, and those numbers do have a meaning. And finally, if your beta is not of that sort, then you would just immediately expect infinitely many. And then plus a natural bijection, a natural set, which is a set of cluster seats to which you want to be bijecting. So, maybe it's true, maybe it's not true, but at least that's something to work towards now. All right. So that concludes my discussion on infinitely many Lagrangian fillings, and I am going to move forward towards the holomorphic symplectic structure. Are there any questions on Lagrangian surfaces, infinitely many Lagrangian fillings, or the sort?
Yes, Roger, you have one question in the chat.
All right.
I can repeat it to you if you can't access it.
I see. Why do you expect only finite many fillings for these links? For this particular kind of cluster algebras, in general, looking at the geometry of things, how the construction works and how you define the cluster variables, it really does seem to me that every cluster seat should only have one Lagrangian filling in it, one embedded exact Lagrangian filling in it. And that intuition sort of comes from other places, from the fact that there's not typically that many exact Lagrangians in a given Coulomb chamber, and at least for these particular cases, which are algebraic links, I really believe that every seat should have at most one Lagrangian filling. And for these seats, for these cluster structures, which are AD and E-type, Fomin and Zelevinsky proved there's only finding many seats. So the short answer is, given the way we obtain the cluster seat, I really would hope that the cluster seat itself determines at most one exact Lagrangian filling. So one Hamiltonian isotopy class. I can elaborate a bit more, but it's going to start. Then it starts to connect to hitching fibers and non-abelian Hodge correspondence, and it kind of goes a bit far away. But yeah, I mean, maybe it's not correct, but we know it for the unknot. I think we can prove it for the Hoffling. So maybe the next test is the trefoil. If we can really prove there's exactly 5 fillings for the trefoil, yeah, then we're probably going to go somewhere. All right.
I just have a quick question too. So just to check, so for these Weinstein 4 manifolds, these infinitely many Lagrangian exact Lagrangian surfaces can what does floor homology say? Like, are they distinguished by Lagrangian floor theory, or?
Yeah, so most of the papers I've written, it's with shift theory, but in my paper with Lenny, there's a floor theoretic explanation, and you can show that the augmentations that they induce are distinct. So you can show the augmentations are distinct with and without loop space coefficients. So when you touch the handle, you kill the loop space coefficients, and you can still show that those are different. So yeah. Another way to say it is if you take morphism and if you look at them as modules over the endomorphism algebra of the co-core, those are different modules. All right. Well, I jump up to understand a bit this moduli space. So this is really a very unexplored moduli space. As that being said, in geometric representation theory, these spaces, in some particular cases, had been studied. And so an immediate outcome is if you happen to be in one of those cases, such as the so-called Lewis case, then you happen to know the cohomology of these spaces. So for instance, things like in the Hodge-Deligne infiltration, that they're of mixed state type, meaning only the KK piece is non-zero. And in the locally acyclic case, which as Jose will maybe mention, it's always the case in the symplectic setting. So M lambda beta is always locally acyclic. Then you actually know the highest part of these guys. So for instance, you take something like the max TB torus 3,4. What is the cohomology of this moduli space that we are naming symplectically? Well, you just happen to know it's isomorphic to variety that they have studied, the top positroid for the Grossmanian 3,7, and then you know exactly what the cohomology is. So as I said, the positroid cases are well studied. Lam and Galashin really have understood this, and they relate to some nice combinatorics. So immediately from the get-go, these spaces that, if you had asked us like 10 years ago, oh, I take the 3,4 torus length, the max TB1, and I compute the augmentation variety, what is the cohomology of the augmentation variety? I think we would all have been like, I don't know. It's a sum-affine variety. But now that we know they have all these cluster structures and they can be identified with those other manifolds, you immediately get that out of the way. So that's something that's proving something we didn't know in symplectic topology thanks to computations elsewhere. So more generally, an interesting aspect of being a cluster A variety or being the coordinate ring being a cluster algebra is that you can define the following symplectic form. A priori, it's just a two form. In a given seed with cluster variables AI, you just take exactly D of AI divided by AI, so AI inverse. This is what this D log of AI means. So that defines a two form for you. And the coefficient in front is just given by the quiver. So the quiver has an adjacency matrix, so you just put exactly the number there. Now, what's highly non-obvious is that this guy that you have just defined in a seed, so if you think of the cluster variety as being something large, and maybe this is just defined in this seed, because you're a cluster variety, the transition functions from here to here are very particular. They're exactly given by the mutation formula. And the way the mutation formula works and the way that this omega s is written allow you to conclude that in the local acyclic case, which we always have, this actually does extend to an holomorphic two form on the whole space, on the spectrum, which in this case contains that. Now, by construction, it is closed. All these coefficients are constant. And then the non-degeneracy boils down to exactly computing the rank of the adjacency matrix of the quiver. So if it's full rank, then upon appropriate quotienting, as I might mention later, you get non-degeneracy. So again, the idea here is by virtue of being a cluster algebra, you end up having this symplectic, holomorphic symplectic two form in your space. Now, this is a form defined really locally. It's a form that I can describe exactly in a chart. The cluster variables give you log their Wu coordinates in each of these charts. But then you can ask, well, do I have a better description for that? Do I have a global description? And I'm going to get to that in a second. So the first upshot here is we get an holomorphic symplectic manifold. That's a good thing to have. It's an holomorphic symplectic, so it's an algebraic variety. For the complex numbers, it has a complex symplectic form. And now we can ask some questions about this. So the first thing, as I said, is in a given seed, that form is very explicit. And how to interpret that form geometrically? Well, suppose the seed comes from a Lagrangian filling L. And then you have this L-compressible system that gives you exactly the variables AI. Then in fact, this particular toric chart, which I was calling TL in the first talk, is just the first cohomology of L with coefficients in C star. If you wish, is ohms from H1 of L comma Z to C star, meaning GL1C local systems. Now, under this simplification, what's happening is that the symplectic form is just encoding the intersection form on the first homology of my Lagrangian. So what's happening is that this L-compressible system provides these AIs, which happen to be exactly log-their-book coordinates by construction. So you have a very good understanding of what this symplectic form is locally. If you are in a chart, that chart comes from a Lagrangian filling, you say, oh, well, that form really is just the fact that H1 of a Lagrangian surface, in general, H1 of any surface, it has a skew-symmetric form. So locally, very, very well understood. The second comment, that's for categorical sort of people who like categories and stuff. In some cases, you can show that some spaces are symplectic by using categorical structures such as a relative Calabi-Yau structure. So I'm going to go a bit fast here. I can delve into that if you want, but there exists the microlocal functor, which takes a given sheaf and computes the microlocal monodromy around its singular support. And you can take the left adjoint of that. You can show it doesn't meet a left adjoint. And then through that left adjoint, if you show that that has a relative Calabi-Yau structure, that's naming some Hodgkin classes and showing some compatibility conditions and non-degeneracy, then you can show, and again, this is all work of Braff and Dickerhoff, you can show that the relative Calabi-Yau structure induces for you a certain Lagrangian morphism at the level of moduli spaces of Toen and Vacquier. And then when you start taking Lagrangian intersections, you end up having a symplectic structure in this particular setting. So the punchline here is there might be some categorical enhancement of this form, but that's not yet been proven that this categorical enhancement would give you exactly the cluster form. Likely, but unproven at this stage. Okay, the last two comments are, well, in fact, if you talk to, for instance, Sasha Goncharov, like it's very interesting how in the cluster world, these forms actually have something to do with the K2 group. And that's mostly just saying that when you take the differences of the forms constructed in each chart, not only like do they match, but the primitive, so it's like zero in some cohomological sense, but the primitive actually belongs to the block group, meaning that the difference is going to be a Sternberg type relation. So x wedge 1 minus x equals 0. So it's very interesting how that can be enhanced, but I don't know how to name that symplectically. The last comment is experimentally, when you compute these moduli and you endow them with these holomorphic structures, you can ask about their Lagrangian skeleton, and that's a way to compute cohomology. That's a way to compute invariance in it. It does seem to be the case that in many cases, such as beta being an algebraic link, that skeleton, that Lagrangian skeleton, has an intimate relation with affine Springer fibers. And there's a sort of heuristic of why that should be true that goes through the Hitching system. But again, non-abelian Hodge correspondence is not something I understand well enough to claim that that's a sort of a general statement, but that would be interesting to explore. Okay, so what I'm going to focus now is to say, we know these things about the construction, and what I've emphasized is that we have this very good local understanding. Given a chart, I can tell you exactly, a cluster chart, I can tell you exactly what the form looks like, but can we find coordinates, global coordinates, where to find it? So this is where I'm going next. What about a global description of this symplectic form? You just look at lambda, you write a formula for a two form, and you say, this is a two form defined in global coordinates. Can we do that? So this is a theorem that we prove with Eugene Gorski, Misha Gorski, and Jose Cimental, which goes as follows. It says, okay, look at your modelized space, M. This is an abstract variety, it's an abstract affine variety, but actually you can coordinatize it rather easily via putting variables for the crossings of lambda beta. So this is going to be a bit quick, but mostly what you do, and Jose will delve into that, is you consider these kind of matrices, which are the identity everywhere except for this 2 by 2 block. So this is exactly at the ith and I+1 row. So in these rows, you exactly put this 2 by 2 matrix, and then claim for you equations inside some affine space for this moduli space M lambda beta are given by this product of matrices being upper triangular. And as I said before, typically you need to quotient by some C star to the K action to make it even dimensional and then get a symplectic structure, not just like a Poisson type or symplectic times C star structure. So that's a very explicit computation. It's written in our paper, in the 2020 paper on algebraic weaves, and it allows you to describe this variety with particular equations. Once you have these particular equations, once you have these global coordinates, zi's are coordinates in affine space, then you can start writing formulas for two forms. And this is what we did. So a suggestion was precisely to do the following. Given two matrices F and G, let's define F bar G by this computation here. So what is happening here, this is the left invariant form in the Lie group. G here is GLN. This is the right invariant form on the Lie group. So you wedge the left invariant with the right invariant, and then you take the trace. And that's a two form in the product of the two Lie groups. And now you have your matrices here that you can use in terms of the crossings of lambda. So what you do is you take the first crossing of lambda, it gives you a matrix. The second crossing of lambda makes you another matrix. You compute this two form. Now you take the first two crossings of lambda, you multiply those matrices, and you take the two form of those two guys with the third one. And you keep doing that until you've multiplied them all except the last one. That's a matrix. That is another matrix. You take the two form associated to them. So this is some computation, and it builds for you a two form, global two form. These zi's are global coordinates. With that being said, they were called like rep coordinates. Exactly, if you like Lagrangian contact homology, these zi's are exactly the rep chords, the augmented values of the red chords under these fillings. So theorem, this form that I just described for you is an holomorphic symplectic two form that is written in our paper, that is precise. And the second statement that's not written in the paper, but it's true, it's somewhere in my Dropbox, is that when you restrict that symplectic form to the space, so this holomorphic symplectic form, it does coincide with the previous one. So what I've done for you here is found an explicit formula based very much on the Lie theoretic nature of these matrices BI, on this description of the moduli M lambda, that allows you to globally describe the two form, and you recover exactly the cluster form in each toric chart. So again, what this really does is use the structure of the Lie group. So the proof goes exactly like that. So why is omega beta closed? This form here closed. And what you do is you compute d of omega, and d of omega, so that's a three form. This is a three form in your space, and it actually is just the pullback of a three form from the Lie group. And that three form is the Cartan three form in SL, well, in GL or in SL1. So this is very natural. What really has happened is that you could just take all the crossings of lambda, multiply all the matrices associated to them in order left to right, pull back the Cartan three form, and that is actually zero in your space. So it has a primitive. That two form that I described above is exactly that primitive. So in general, what's happening is that the equations for my variety, the equations that I said in the previous slide, are exactly being upper triangular. And the Cartan three form vanishes for upper triangular matrices. Therefore, d of omega, which is the pullback of the Cartan three form, must vanish as well. So that closeness is sort of very easy to state because of the way things have been constructed, which was sort of non-trivial. Now, non-degeneracy is a harder check, and that needs to be done more carefully, and that is done in our paper. And now the comparison with the cluster form, that is an induction process, which, it's not too bad once you know what you're doing. But yeah, it's also something that needs to be checked. I don't know a general principle for which these two things should coincide. You just check they coincide in Lagrangian fillings, and then you're kind of good to go. All right, so this is my last comment on sort of symplectic topology of these spaces and studies of these spaces. And now I'm going to sort of switch gears in that now I'm going to say, well, suppose you know all this symplectic topology, you've proven the results you have with symplectic topology. what can you say about cluster algebras? But given the nature of the audience, maybe it's also a good point to stop and ask for any questions or clarifications you'd like with regards to this first part. All right, okay. So now we switch gears. Now we're going to become rather algebraic. So suppose somebody from cluster algebras comes to you and says, I have this space. Maybe the space is a double Brouwer cell, maybe it's some unipotent cell, maybe it's a positroid, maybe it's some nice space that people have studied in geometric representation theory or in combinatorics. Is it a cluster algebra? Well, they have their methods to try to prove that, which oftentimes succeed, but they not, it's not completely general, and they have spaces for which they don't necessarily know the answer. And now you can try to say, well, maybe those spaces do appear as moduli spaces of Lagrangian links. And the simplest example where this situation occurs is Richardson varieties. So for any Lie group G, you have the flag variety G mod B. You can define Schubert cells. You can intersect a Schubert cell associated to a permutation U with a Schubert cell, the opposite Schubert cell associated to a permutation W. You intersect, you get the Richardson variety. You can ask, is the coordinated ring of that a cluster algebra? And that is something we can prove for simply connected simple Lie groups, simple Lie groups, sorry. And how does the proof work? Well, mostly the moral of the proof is, if I'm interested in knowing that a space is cluster, maybe I can find a lambda beta such that X is isomorphic to M lambda beta. Then by our symplectic work, M of lambda beta is cluster, therefore X is cluster. Now, this is sometimes simple, this is not simple. So for instance, if you take the case of the double Bott-Samuelson cells that Dapping was discussing, he explained to you how to build those Lagrangians. Those are exactly the rainbow closures of positive betas. But if you take a Richardson variety, already in the SLN case, actually, this is not the moduli of a Lagrangian, which is the rainbow closure of a positive beta. But it is nevertheless the -1 closure of a positive beta. So this is a case where the work of, so what Jose will explain, which is the work we did with Eugene Gorski and Misha Gorski and Jose and company, is relevant. So this is the case where you really need the -1 closure, not just the rainbow closure. So Richardson varieties do not fall within the Bott-Samuelson cell case. They do fall into the more general braid variety case. So now, nice proposition. Suppose you want to build a Lagrangian lambda such that the moduli space is exactly the same as the Richardson. Well, how do you do that? There's not much combinatorial information given to you. You're given two permutations, U and W. And morally, what you want to do is you want to take W, U inverse, and maybe you need to adjust because of the -1 closure with the delta square. But you're trying to draw a front. And so this W inverse does not make sense. So you end up doing a little trick, which is to say, well, U inverse doesn't make sense in the front, but this is a positive word. This is equivalent to a positive word. Like it has negative crossings, but you can always write delta such that, write delta in a way that it's like U times delta prime, say. And then when you multiply by U inverse here, U inverse, this is just delta prime. So this is what I meant by this, like delta divided by U. So the point is, this is a positive permutation, this is a positive permutation, this is a positive permutation. You can take the -1 closure of that and then check by hand that the moduli of sheaves is exactly the Richardson variety. Therefore, by what we've been saying, this is actually cluster algebra. That's sort of a quick explanation of why Richardson is a cluster from the symplectic perspective. Now, as I said before, this does work for any Lie group. And it also does something when you're studying the incompressible systems behind this construction, which is it's not so obvious that what you get is a unique cluster structure, but rather there's a series of choices in the construction, and different choices give you what's called a quasi-equivalent cluster structure. So this is work of Chris Fraser initially, and then Chris Fraser and Melissa Sherman-Bennett, that actually emphasize that quasi-cluster automorphisms, quasi-cluster structures are a bit more natural than cluster structures. And indeed, from a symplectic perspective, you should always say quasi because there's often choices in the construction, and the only thing you can say is that at the end things are quasi-equivalent. I should maybe mention the notation is confusing. A quasi-cluster structure is always a cluster structure. So a quasi-cluster structure is more like a lot of cluster structures, and you don't have a preferred one among those collections. So yeah. So actually having a quasi-cluster is in a sense stronger than having cluster. Like you have more choices, and that's great. The second comment is, in general, what we're trying to do here is think about inverse problems. It's like you're given some problem in algebra, and you're trying to find geometry that will lead to that problem once you consider Fukaya categories, shift categories, moduli spaces. So here, you were given this algebraic variety. Can you realize it as the moduli of sheaves in a Lagrangian? You can play that with any object. You can say, suppose I give you an automorphism of this variety. Can we realize it via Lagrangian loop? In general, suppose I give you the positive part, the tropical part. What is the right symplectic topological object to look at so as to understand that? Same with the theta basis. So in general, as I tell my students, like the process, the business of studying geometric realizations is a lucrative business. So whenever you find like some map, which is very interesting algebraically, if you can realize that as a contact isotopy, as a symplectic covariatism, as a Lagrangian covariatism, you're going to learn things. And usually the algebra becomes very much transparent if you've been able to geometrize it. A beautiful example of that is, for instance, the periodicity of the Donaldson-Thomas transformation for torus knots is completely apparent because there are Lagrangian loops. But it's completely not obvious at the cluster setting. So again, the geometry really visually allows you to prove some algebraic formulas that way. All right. So I did mention the Donaldson-Thomas transformation. If you're in the world of geometric representation theory, of Donaldson-Thomas transformations are relevant, and in particular for cluster algebras, you can ask the question, does a Donaldson-Thomas transformation exist or not? Sometimes they do, sometimes they don't. There are combinatorial characterizations to do Bernard-Keller in terms of reddening sequences or green to red sequences, which is slightly stronger. And you know, sometimes you can find them directly, and sometimes you just don't know whether they exist. Luckily, in the process, again, by the explicit nature of how we constructed things, for these moduli spaces and these cluster structures, we can show that Donaldson transformations exist. And furthermore, we can explain what kind of contact transformation, it's a combination of a Lagrangian isotopy and then a contact homomorphism, you need to do so as to realize the Donaldson-Thomas transformation. And in general, what happens, and this is an observation of Gao Sheng Wang, the square of the Donaldson-Thomas transformation is actually the Lagrangian loop that I was describing at the beginning of the talk that takes the box beta and moves it all around. So again, not only the DT exists, but it's very well understood geometrically now. Like we really can induce it through these contact isotopies or Lagrangian loops. Okay, as maybe going over the case of dapping, in the Bott-Samuelson case, this is actually a green to red sequence. In the braid varieties case, you cannot find that. It's just a reddening sequence. But again, by the combinatorial criterion of Keller, that is enough to conclude that something is Donaldson-Thomas transformation. Now, great. Okay, so there's a special transformation that some people care about. It counts some invariant somewhere if you package it the right way. What else can you say? Okay, why is Donaldson-Thomas good? Well, there's a nice statement of GHKK, Gross-Hacking, Killing, Tsevich, that actually states that when you have a cluster structure for which the Donaldson transformation exists, and you're full rank, which we are in many of our cases, then you can actually find, then you can deduce the duality conjecture, but in particular, you can actually find canonical bases of theta functions. And those are naturally parameterized by the tropical points of the dual algebraic variety. So now you could ask, okay, you've given me these cluster variables. Can you give me a basis for the algebra, the whole algebra? And Gross, Hacking, Kontsevich, and Kiel explain how to build this basis of theta functions by the broken lines technology. And what's interesting is each element of that basis is parameterized by a tropical point in the dual variety. And in our setting, the dual variety is itself also a braid variety. So we end up working with a set of varieties that works very well. You can just take the line-length duals of the group, still consider the same flag configuration for the same beta, and then that is what's called a cluster ensemble. And the fact that DT exists, well, it's beautifully, it's a beautiful result on its own if you know about what DT is. But even if you don't care, that allows you to prove the cluster duality holds. So it allows you to build these theta functions, and it allows you to sort of see really this version of mirror symmetry in terms of the flags themselves. Okay, so that's another type of inverse problem. And finally, a couple of comments. As I said before, cluster algebras, typically, if you look at the book of Fomin and Williams and the work of Fomin Zelevinsky, the starting papers, cluster algebras are often named via combinatorial object. They either give you a wiring diagram, or they give you a Plavix graph, or they give you maybe the quiver directly. How can you describe seeds which are very far away? All these combinatorial objects, what they do for you is they name a seed. But maybe I want to access a seed which is like 7 mutations away from it. How can I describe that? And there's been some interesting work, and Chris Fraser is somebody worth mentioning here, where he studied SL3 webs so as to maybe access other seeds. But one thing that weaves do for you is accessing seeds that a priori Plavix graphs cannot. So this is a Plavix graph for the Grassmannian GR36. It's a reduced Plavix graph. And if you wanted to mutate at this phase, because it's a square phase, you can mutate there. You can also mutate in this one. You can mutate at any of the faces which are square. That's something that Plavix graphs are good. You can design, they're kind of designed for that. You just change the black vertices by the white ones in the square phase and you're good to go. But now you say, okay, well, in fact, this central hexagonal phase gives you a vertex of the quiver, which is mutable. That, if you look at the top positron for this guy, like that guy is mutable. Can I find another Plavix graph obtained by mutating at this phase? Sorry. And the answer is, well, I think the answer is like, we just don't know. Like, we don't know whether one can mutate and describe it in any combinatorial way with something that has to do with Plavix graphs. I mean, if you just look at the relation, the new variable for this guy in the middle, the mutated variable there, is going to be quadratic in the Plucker coordinates. So it's not going to be a Plucker coordinate itself. So it cannot just be a Plavix graph. So we know that whatever mutation we do at this phase, it cannot be a Plavix graph. Now, you do that with weaves, and what you realize is that the central phase is just this white tree in here. And if you look at one of the images of my mutation in the first talk, it's perfectly fine to mutate there, and you get a new weaves. So what weaves allow you to do is, in many cases, they give you a combinatorial model that describe a cluster seed. They describe these initial seeds for you, but they allow you to mutate to another seed, still being a weave. So what the Plavix graph is not able to do here is describe the new weave with a Plavix graph. Sorry, the new seed with a Plavix graph. What the weave allows you to do is you start with a seed given by a weave, and you can mutate somewhere else, still described by a weave. And the faces don't have to be square in any sense. So a general comment on that is that the geometric statement behind that is actually significantly stronger. It's a statement about the fact that reduced Plavix graph, grid Plavix fences, ideal webs of Goncharov, they all can be translated into weaves. And actually what's happening is really a symplectic thing, because what you can do is consider the conjugate surface associated to the Plavix graph as a Lagrangian surface. And my claim is, and this is joint work with Wen-Yuan Li, this is already available on the archive in a paper called something like Conjugate Lagrangians and Weaves. You can translate the conjugate surface into a weave. And in fact, for all these collections, all these examples, these 4 moves suffice. And so what you end up proving is that those conjugate surfaces, which were encoding something about the Plavix graph, are actually all weaves. And more generally, weaves will allow you to mutate where conjugate surfaces will not. You wouldn't stay the conjugate surface of a graph. So that is some, like, again, purely geometric statement about some surfaces being Hamilton isotopic, but it has all these consequences for you at the level of cluster algebras. All right, so my last comment is, there's many directions forward. Maybe I'll wrap it up somewhat quickly, but I'll just mention them. Number one, develop a systematic theory of L-compressible system. Can you classify them? Can you say, okay, if I give you this curve in the Lagrangian filling, how many disks are bounded by this curve? So on and so forth. Another question is, okay, we explained that these Lagrangian fillings give cluster seeds. Is this surjective? Is this injective? Is any cluster seed inhabited by a Lagrangian filling? Is it possible to have two Lagrangian fillings that give you the same cluster seed, even if they're not Hamiltonian isotopic? In particular, address the ADE conjecture. So these are all questions kind of in different directions. So another one is a more geometric question. Well, I discussed these lambda beta Legendrians. What about a Legendrian that's not of the form lambda beta? Well, there you already have the issue that the moduli space is not an affine variety. It's a derived stack, which is kind of a nice kind of derived stack, but we don't have a notion of cluster derived stack, nor a notion of sort of what a cluster category is. I mean, I know there's categorifications of cluster algebras. I know there's something called a cluster category, but what we don't know is a categorical definition of a category being cluster such that the moduli of tau and vacua is itself cluster. So that's more of an algebraic question for people out there who would like to generalize the notion of clusters to derived stacks or maybe to categories, which seems to be what naturally appears in symplectic topology. Question 4, I did mention that there was an holomorphic symplectic structure. Try to find holomorphic Lagrangian skeleton for that. And more generally for these moduli, as Dapping mentioned, one of the aim groups in January was trying to understand compactifying potentials. You can compactify this manifold per every word beta to a Brigg manifold and compute potentials for that. That's interesting. That sounds doable, but a lot of beautiful geometry should come from there. And finally, as a general comment, maybe it's somewhat related to what Mohammed said, you start with a symplectic 4D version. You know, it's just symplectic 4-ball, Lagrangian surface in it. Okay, now you go to this B side, the mirror side, this is the space that parameterizes Lagrangian fillings, and this is some higher dimensional algebraic variety. Well, what can you possibly do to start on the B side, to start with this, like, the positroid cell in a Grassmannian, maybe with some additional data, and actually do something to end up naming a Legendrian or maybe a Lagrangian surface for the 4-wall. So like, what's the right way to go the other way around in the mirror symmetric sense? And I truly mean it non-homological here. I'm not asking questions, which is interesting, about like, does the partial Raffo-Fukaya category recover lambda or things like that? I'm really asking, what kind of moduli should we be considering in M lambda beta so as to recover anything similar to like D4 comma lambda beta? So anything in that light, I'd enjoy hearing ideas about that. Well, thanks a lot. Thanks for listening again. That's the end of the application section, and Jose will now prove for you the general result. Thanks a lot.
Okay, great. So let's thank Roger. Okay, so questions. So you have one question in the chat.
Yeah, so the short answer is I don't know about the hyperkiller metric, but that's a limitation of mine. It might be that people actually can say something about it. And about the holomorphic Lagrangian fibration, I also cannot say much, except if you're okay with non-abelian Hodge correspondence, then this should be a hitching system over P1 with one irregular fiber. So say you have an algebraic knot, then you should be able to write that as a hitching fibration over P1 with one really irregular fiber over which you have the compactified Lagrangian, sorry, the compactified Jacobian. And so you're going to have that the total space has this Lagrangian fibration and it retracts onto this central very singular fiber, which is the compactified Jacobian. And it is the connection with the fine Springer fibers that these compactified Jacobian have, for which you would say, oh, that's why this should be a good holomorphic Lagrangian skeleton. So the short answer is they should exist, but as far as I know, you kind of have to go through non-abelian Hodge correspondence to name these Lagrangian fibrations.
I have actually like a naive question. So in this process you were describing for going from a cluster variety to sort of like reverse engineering a Lagrangian from it,
Mhm.
how generally do you expect that to work? Like, are there examples of cluster varieties where it clearly can't be given by a moduli space from Lagrangian, or is there some kind of given a cluster variety does it, should it have some nice properties for you to expect that this process might work, or?
I mean, depends on how much generality you want. So if you're studying really Lagrangian fillings in the four-ball with this kind of Lagrangians, most of the varieties like would come as like smooth affine varieties. So cluster varieties in general, like it could be very singular. This coordinate ring only sees up to codimension 2. So you have like a singularity, which is like codimension 7 or something. You're not going to see that. So that's one thing. Another thing is just the combinatorics of the type of quivers that you get. As I said, they're locally acyclic, and many of them have the Lewis property. So any cluster algebra that is associated to a quiver which is non-locally acyclic, we know it cannot come from Lagrangians in S3 bounded by the four-ball. Now, could we do that in, attach a bunch of one handles or something? So like in a Lagrangian in S1 times S2 or a connected sum of them with a different filling, or don't have the four-ball, have a more general Weinstein manifold. Could that allow us to access more weird things? I would say probably. But yeah, I mean, on the one hand, we've seen phenomena, say, the paper of Ivan Smith about Fukaya categories and quiver categories. Fukaya categories can get as bad as any quiver category, which is kind of saying a lot. So in that sense, I would expect some kind of construction saying for this kind of quiver or these kind of things, you might be able to build a symplectic setup that realizes it. But yeah, at the same time, for the four-ball, yeah, I think you can discard things immediately by, say, naming something that's not locally cyclic.
I see. Any other questions? Okay, you have another question?
Yeah.
In the chat.
Yeah, the answer is I don't know. I don't know any reasonable criterion. I'm sure there's some silly obstructions at the formal level, at this sort of, if you know that there's a Lagrangian which is not of the form lambda beta, but like some complicated thing, and then you can maybe say, oh, the number of swallowtails that you need is like even or something. So the number of swallowtails in a D4 minus is 3. So you always have a multiple of 3 number of swallowtails. So there's probably algebraic topological obstructions that tell you in some cases that some Lagrangian fillings are not a weave. Now, in the case of Lagrangians lambda beta, all this obstruction vanishes. So I have no reason to believe currently at the level of H principles that a Lagrangian filling for lambda beta should always be equivalent to one coming from a weave. I'd love to have an example showing that that's not the case, but there's no obvious obstruction that I can cook up saying that that's not the case. So for all I know, they're all weaves. May I ask what the braid looks like for the dual cluster variety? The braid is the same. It's just you now take flags in the Langlands dual group. So say you're working in like SL. So flags in SL is just like, SL mod upper triangular matrices in SL with like ones in the diagonal. Like then the flags are just there, right? And now when you take the Langlands dual group, you just exchange SL by PGL. And so now you have flags in PGL mod, which is the same, right? The flag variety is kind of the same, just like sort of the root system has changed according to this duality. So the braid stays the same. It's just sort of, you now change everything to be in the Langlands dual group.
Okay, so first let's thank Roger one more time. And so I guess the next and final talk will be at 2:30.